is the strongest material we know, the ultimate material, which is actually not designed, but it has been there all the time.
Your suit, vibranium?
Wakanda forever!
Vibranium, yeah, strongest metal on Earth.
Vibranium. It's completely vibration absorbent.
We all know that in the Marvel Universe, vibranium is this insanely special material. It's used in Black Panther's suit, it's what Captain America's shield is made of, and it's basically the foundation of all Wakanda technology. That's why Wakanda ends up being the most advanced nation on the Marvel Universe.
There's vibranium on those trains?
There's vibranium all around us.
But that's Marvel. So what about the real world? Does vibranium actually exist? Short answer is no, guys. Vibranium is completely fictional. It only exists in the Marvel Universe. But this wouldn't be Entropian if we stopped at fiction. Because the crazy part is, in the real world, there is a material whose properties sound way too close to vibranium to ignore. This thing is often called the thinnest material ever discovered, yet somehow it's about 200 times stronger than steel.
This material is the strongest material we know. It's stronger than diamond.
It's the strongest material ever measured. The implant carbon bond is stronger than the tetrahedral carbon bond in a diamond. At the same time, it is flexible and stretchable.
There's even this famous illustration where an elephant is standing on top of a pencil, and the pencil is resting on a sheet of this material, and it still wouldn't tear. Yeah, this material's strong as hell, but somehow it's still flexible. And here's where it gets even more wild. NASA has actually considered using this material as the main component for a space elevator, a structure that could stretch from Earth all the way to outer space. So what is this material? And how close is it really to being real-world vibranium? Let's talk about it. Alright guys, before we go any further, there's something we need to get straight. What makes vibranium look absolutely insane isn't just the fact that it's strong. What makes vibranium different is how it deals with energy. It doesn't blast energy out like Thor's hammer or some glowing laser beam. Instead, vibranium makes Black Panther's suit and Captain America's shield survive hits that should have wrecked them. Because all that energy doesn't get reflected, it doesn't get released, it gets absorbed. And that is what makes vibranium so special.
It's not just a metal. They sew it into their clothes. It powers their city, their tech, their weapons.
It's actually so special that Wakanda literally had to isolate itself from the rest of the world because way too many people were trying to get their hands on vibranium. But now here's the real problem. In the real world, there is no such thing as a material that can take endless hits with zero consequences. If something gets hit, something will happen. Maybe it heats up, maybe it deforms, or maybe it slowly starts breaking down. In other words, every real-world material has a limit. Doesn't matter how advanced it is, if you keep pushing it, sooner or later, it reacts. And that's where reality starts to clash with vibranium. Once you look at all those limits, it's pretty obvious that vibranium can't actually exist in the real world. That kind of material just isn't possible. But out of all the materials we know today, there is one that scientists keep saying comes the closest to vibranium. And that material is...
This is a material which theorists like I have said this is impossible.
It's the strongest material ever measured.
Known as graphene.
Graphene.
And it's known as graphene.
Yep, graphene. According to a lot of scientists, graphene is one of the most revolutionary materials of the future because its properties make it insanely useful for tons of applications. In a lot of ways, it really does feel like real-world vibranium.
Graphene is the new future. Why? Well, because it's perfect for so many different applications.
And the most absurd part? Graphene comes from something that looks completely unremarkable. It's come from a pencil. Yeah, an actual pencil. The thing that we used to write with in school. Because graphene comes from graphite, the same material that makes up the tip of a pencil. And that raises a really weird question. How does something that starts out fragile and boring turn into one of the strongest materials ever discovered? The answer shows up when you look at how graphene's atoms are arranged. The story of graphene starts with two scientists, Andrei Geim and Konstantin Novoselov. In 2010, their discovery was so important that it earned them the Nobel Prize in Physics. And what's funny is, their experiment wasn't high-tech at all. No expensive machines, no secret technology. It's just graphite and tape. Seriously. They literally kept pressing tape onto graphite and peeling it off over and over again, until eventually they were left with a single, ultra-thin layer. And that layer is what we now call graphene. So now comes the big question. Why is something this thin so insanely strong? And the answer comes down to how graphene's atoms are structured. If you've ever seen the atomic structure of most materials, you'll notice one thing pretty quickly. Almost everything is built in 3 dimensions. Steel, aluminum, titanium, their atoms bond in every direction, forming thick and solid structures. And that's normal. That's how basically all everyday materials are built. But graphene is different. In graphene, the atoms, which are carbon atoms, are arranged in a perfect hexagonal pattern, look like a mesh or a honeycomb. Graphene is essentially a 2-dimensional sheet of atoms. That's why it's called the thinnest material in the world, because its thickness is literally just 1 atom.
It's only 1 atom thick.
It's the thinnest of all materials, only 1 atom thick.
And this unique atomic structure is what makes graphene special. Some people even go as far as calling graphene is a real-world vibranium. So let's break down how graphene and vibranium are actually similar, one by one. So let's start with the most obvious property first, the strength. Based on testing, graphene has a tensile strength of around 130 gigapascals. Now let's compare that to steel. Take galvanized steel, for example, the kind used to support structures like the Golden Gate Bridge. That type of steel has a tensile strength of about 600 megapascals. And when you put those numbers side by side, it gets kind of ridiculous. Graphene ends up being roughly 200 times stronger than that steel, even though graphene is only 1 atom thick. And this lines up perfectly with how vibranium is described in Marvel. Vibranium isn't strong because it's thick. It's not strong because it's heavy. It's strong because its internal structure is extreme. And graphene works the same way in the real world. It doesn't win by size, it wins by atomic structure. And besides being insanely strong, graphene is also ridiculously light.
There is a layer of graphene on a transparent substrate. I can see you all through it.
For perspective, imagine if you covered an entire football field with a single sheet of graphene. Now guess how much that sheet would weigh? It's just 1 gram. Yeah, 1 gram. To cover a whole football field, you'd only need 1 gram of graphene. That's even lighter than a couple of paper clips. And vibranium is always shown like that too, right? It's used for armor, shields, vehicles, because it's not heavy or stiff at all. So another clear similarity is that both graphene and vibranium have a completely absurd strength-to-weight ratio.
No, that's just a prototype.
What's it made of?
Vibranium is stronger than steel and 1/3 the weight. It's completely vibration absorbent.
Now in Marvel, vibranium can absorb kinetic energy, which is why anything made from it is basically bulletproof or even can against explosions. And in the real world, graphene shows something surprisingly similar. In microballistic tests, where graphene layers are shot with tiny projectiles, it showed that the impact doesn't stay in one spot. Instead, the force spreads out across a wider area. So it's not just blocking the hit. Like vibranium, graphene can manage and redistribute impact energy.
We shoot this sphere at a very high rate, around 1 kilometer per second. And because graphene is very, very strong, this cone spreads out to quite a distance in the material. And the kinetic energy of the sphere is transferred to the membrane before it pushes through and then eventually exits on the other side. And when we compare the behavior of graphene thin films to that of other materials, for example, steel, on an equal weight basis, graphene is 10 times better than steel at absorbing energy out of micro bullets.
Vibranium. It's completely vibration absorbent.
And there's another property that makes graphene even more insane. Graphene is one of the most electrically conductive materials ever discovered. Because its atomic structure is flat, clean, and perfectly arranged, electrons can move through it incredibly fast, way faster than they can through copper.
And because of its particular atomic structure, which has these carbon atoms that are bound together in a hexagonal structure, it is actually extremely good at conducting electricity. And this is what we need for electronics. We need conductors. Now,
That's why graphene is now being developed for things like supercapacitors. If that tech works at scale, stuff like battery health anxiety could basically disappear. Charging times could drop from hours to minutes or even seconds.
What I'm holding in hand is one prototype we have made, the graphene supercapacitors in our lab. With graphene supercapacitors, we are able to fully charge our vehicles when we are buying a cup of coffee. And we can do more than that. We can put that onto electric aircraft, reduce the weight, and let them travel a longer distance.
They're amazing, absolutely amazing.
Graphene is also part of something much bigger. It's part of nanotechnology. And fun fact, even in Marvel, vibranium itself is treated as nanotechnology through what they call nanites.
The nanites absorb the kinetic energy and hold it in place for redistribution.
Very nice.
And Tony Stark's latest tech uses that exact same concept.
Where'd that come from?
It's nanotech. You like it?
We'll break down nanotechnology in the next video. It's going to be a wild one. So don't forget to subscribe, turn on notifications, and make sure you don't miss it. But guys, no matter how insane graphene is, and no matter how close it looks to vibranium, we still live in the real world, not the Marvel universe. In Marvel, vibranium just shows up because an asteroid crashes into Earth. So Wakandans don't have to worry about making it, they just focus on using it. But in real life, graphene doesn't fall from the sky. We have to manufacture it. And that manufacturing process is exactly why graphene still hasn't made its way into everyday life. Because graphene is ridiculously thin, we'd need millions of layers just to reach a thickness of 1 millimeter. Which means even if we want to make graphene that's just a little bit thick, we'd have to stack layer after layer with insane precision. And that's the problem. In the real world, maintaining that level of precision at large scale is brutally hard. One tiny defect, one misaligned layer, one small structural flaw, that's already enough to seriously mess up graphene's performance. So even though graphene looks incredible in the lab, the moment you try to mass produce it, the challenges pile up fast. Not because graphene isn't amazing, but because reality isn't as forgiving as the Marvel universe. But that doesn't mean the story ends here. Even though graphene is still expensive, hard to produce, and nowhere near ready for mass adoption, a lot of scientists agree on one thing. Graphene is a time problem. And when that time comes, graphene could realistically replace things like batteries, bulletproof armor, and even major infrastructure materials. And then there's the most extreme idea of all, an old concept that's starting to resurface again. NASA's idea of building a space elevator, a structure stretching from Earth into space.
So if we launched a satellite and put it directly above us two now, then it would be directly above us forever, always. Then the idea is, you take a cable from that satellite and drop it all the way down to the ground. So we have a cable now coming down between us. We can then climb up that cable and we're in space. That's the idea of a space elevator. It's quite simple to explain, really hard to do. It would probably be one of the biggest engineering projects of humanity.
Something that used to sound completely insane is now being talked about seriously again. Why? Because one of the biggest problems finally has a potential answer. What material should be used? A space elevator needs a material that's insanely strong and insanely light, because nobody wants that thing falling back down to Earth, right? And out of all the materials ever proposed, graphene is one of the few that actually makes sense, at least on paper.
And we've got something called single crystal graphene, which is emerging from the research labs. And looking at the properties, the mechanical engineering properties of that material, it looks as though it's going to be strong enough to do the job.
If you ask me, will this ever happen? Maybe, I don't know. But the fact that this idea is being discussed seriously again tells us something important. That graphene isn't just hype, it's special. So in Marvel, vibranium is basically the answer to everything. It comes from outer space, it's perfect, and it's ready to use. But real life doesn't work like that. In the real world, things are way messier. We don't find perfect materials. We only find a small clue, tiny steps pointing in that direction. And graphene is one of those steps. It's not vibranium, it's not indestructible, and it's not ready to be used everywhere. But for the first time, humanity is seeing something interesting, that a combination of properties we once thought only existed in fiction can actually show up in the real world. So yeah, maybe vibranium will never exist, but the direction toward it, we can finally see it now.